Hello kids. So in this video, this should be the second video that you're watching in your February break. Hope you're having a nice break. Hopefully you watched the first video, which would have been part 2 of the kinetics lecture, which would have discussed integrated rate law, which you actually will need to understand the content of this lab experiment that I'm about to explain to you, okay? So this is a theoretical walkthrough of the lab that you would have done, actually a combination of multiple labs, but I'm going to explain the principles of spectrophotometry to you guys and explain Beer-Lambert law, and then walk you through what this lab would look like in a kinetic scenario, okay? So first thing is we have to understand what spectrophotometry is. So spectrophotometry, which is a long word to write, is basically using light to analyze a compound, okay? You can apply this to a lot of things. You can have a solution that has different concentration of cells in it, and you can use light to figure out what the concentration of the cells are, or some kind of enzyme or a byproduct. You can use spectrophotometry for a lot of purposes in a research lab, okay? It's a super important analytical technique, and it's something that usually pops up on FRQs. And Beer-Lambert law is the law that is associated with this principle of spectrophotometry, okay? So spectrophotometry is done using a spectrophotometer, which those are really expensive, but they are very finely tuned pieces of equipment that are very useful, okay? We don't have spectrophotometers. Instead, we have kind of a baby version of it called a colorimeter. And it functions as a basic spectrophotometer. It does the things that we need it to do, and it does it pretty well. So far, all the labs we've used, the data we've gotten for this particular lab, it has been really great, okay? So this colorimeter right here, this black kind of spherical thing, it's the exact one that we use in school, actually. And you'll notice that it has 4 settings. It's kind of tiny on this video, but you'll notice that it has 4 settings, and those are the 4 wavelengths that you can set this colorimeter to. And that's basically its main weakness, that it doesn't have a broader range of wavelengths, okay? A regular spectrophotometer could go anywhere from 0 to like 1,000 nanometer wavelength. You can vary anywhere. But here it's like exactly like 4 set wavelengths right there. That's where you were looking. There you have to set it to. Okay, now this is the exact setup that we have. This actually connects to a little vernier probe where on the screen you'll get like numbers that this colorimeter is going to spit out, okay? So this little transparent rectangular thing is called a cuvette. Kind of a cute name, okay? It's called a cuvette, and it's got a little lid. We fill this up with solution, we close the lid, and then we put it inside the colorimeter. We close this lid, and we take a measurement, which will appear here, okay? Percent T is percent transmittance, which I will explain as we go through this walkthrough of the lab, okay? And usually you would calibrate the colorimeter with something that is like your control for the lab, okay? Usually a control is a cuvette filled with distilled water where there is nothing in there. It's just pure distilled water. And it tells us, and it gives us like a baseline measurement for what it would be if there was nothing in like a solution, okay? So let's look at what is happening inside the colorimeter. So inside the colorimeter, there's a light source, and that light source is releasing visible light, actually, okay? And there's a lens. So this is the light source. It releases wavelengths of visible light. And there's a lens. The lens is actually able to concentrate the light into a more narrower beam so that it's not getting scattered everywhere, okay? So it narrows it down, And then they have something, I don't know what exactly is in this colorimeter, but they have something that is able to split apart that white light. So visible light, when all the wavelengths are together, is white light, right? But if you use something like a prism or some kind of diffraction grating to diffract the light, meaning bend the light, okay, the wavelengths will separate into the colors of the rainbow, basically, right? And then you have some kind of filter that takes that light, and you can adjust the filter to filter out all the wavelengths except for the one that you want, okay? So, for example, if I wanted to only let this wavelength pass through, this is 430 nanometers. If I only wanted wavelengths that correspond to that wavelength pass through, or light waves that correspond to that wavelength to pass through, I would adjust the filter basically in the colorimeter. I would press the button, and the filter would basically filter out all light except for that particular wavelengths, or the wavelengths corresponding to that color light. Okay? Then that light passes through the slit in the filter, and it'll go through your cuvette. This is your cuvette. And come out the other side, and then whatever comes out the other side is detected by a detector, and that detector gets transferred to some number here, which is called transmittance. Okay, so colorimeters are used for collecting something called transmittance. It's basically what the word means, like the definition is in the word, okay? You are transmitting light through a sample solution. Some light goes in. Some of those wavelengths that you are putting into that is absorbed. Okay? Some of that is absorbed. And whatever is not absorbed by whatever compound is inside the cuvette is transmitted out the other side. So some light gets absorbed, some light gets transmitted, and whatever was transmitted is read in this little display right there. Okay? Usually it will either display percent transmittance or transmittance as a decimal, whichever one is the same thing, right? Okay. So light source, you split the light source into different wavelengths. You use your filter to pick which wavelength you want to pass through the solution. The solution absorbs some of that light. Some of it is transmitted, and you get your reading there. Okay? So think of it intuitively. The more concentrated the solution is, the greater the absorbance. So the lower the percent transmittance. Less light is transmitted through, the more concentrated a solution is. And in order for this kind of thing to work, okay, for you guys in a colorimeter situation for Beer's Law labs, all solutions must have color. Must have a color. So the two solutions that you actually use this for in a regular year would be a copper sulfate solution, which is blue, and then the crystal violet, which is this lab, is purple, okay? Without colored solutions, you cannot use colorimetry, okay? It's actually a common question during AP exams to ask, oh, the student wanted to use Beer's law to measure concentration of sodium chloride. Why did it not work? Well, because sodium chloride has no color, it's a clear colorless solution, and therefore colorimetry or spectrophotometry cannot be used to measure concentration, okay? Now, that's not to say that those solutions do not absorb light. Those solutions do absorb light, except it's not maybe in the visible light spectrum, okay? It might be infrared light or UV light or microwaves that those solutions are absorbing, but it's not visible light. And Beer's law deals with visible light in our case, okay? In colorimetry, it's visible light spectrum that we are dealing with. So I think 400 to 700 nanometers, that range, okay? All right, so now that you know how a colorimeter works, let's talk about transmittance, absorbance, and Beer's law, okay? So this percent transmittance is basically a ratio between the light that goes into the solution. Okay, let me erase some of this right here. Okay, so it's a ratio between the light that is sent into the solution and the light that actually comes out of the solution and then is collected by the detector, and then the number shows up on the screen. Okay, so you can say that transmittance is equal to the amount of light that came out over the amount of light that came in, okay, or went in. Usually, sometimes you'll see in textbooks and notebooks and online sources that this is IT, but sometimes you'll see it's just I. So I over I naught is equal to transmittance. So I is the amount of light that came out, and IO or I naught is the amount of light that went into the actual cuvette, okay? And that light will be of a specific wavelength or a specific range of wavelengths, all right? Now, you calculate percent transmittance by just multiplying this number by 100. So percent transmittance is equal to this ratio times 100%, and then you get your percent transmittance, okay? Now, if you have something like water inside the cuvette, like distilled water has nothing in it, so you would get 100% transmittance. All the wavelengths of light that you are sending through the distilled water cuvette will actually end up being transmitted. So I naught and I are the same thing for distilled water. You would get 100% transmittance, okay? So this is why we use distilled water as our control, because distilled water tells us that if there's nothing in the solution, this is the amount of light that will be transmitted, which is 100%. If you have something that is like different solutes inside your solution of different concentrations, the greater the concentration, meaning deeper the color, the less light would be transmitted because more light would be absorbed, okay? More particles or more moles in the solution means that more light will be absorbed by those particles and less light will be transmitted, okay? So this is often called the reference blank. And we always say that in between obtaining the transmittance for different concentrated solutions, you actually have to use the reference blank to calibrate your colorimeter. So in a lab situation, the first thing you do is you put your distilled water cuvette in here, you close the lid, you hit calibrate, and then this screen will read 100% transmittance, which means your colorimeter is now calibrated to read the water as being 100% transmittance, okay? Now, for most chemical and biological experiments, we measure not just transmittance, but in fact, we measure absorbance, because absorbance and concentration actually have a linear relationship, okay? And we want a linear relationship because it makes our lives much easier to have that to use in our calculations and whatnot. But the relationship between absorbance and transmittance is a logarithmic relationship, and the absorbance is actually equal to the negative log of the transmittance. So the actual instrument will give you percent transmittance. So you take your percent transmittance and you divide by 100 to get your transmittance, okay? Because you're just turning the percentage into a decimal, okay? So percent T divided by 100 equals just the transmittance as a decimal, or as out of 1, okay? So the negative log of the transmittance is absorbance, okay? And if it's 100% transmittance, this is transmittance, for your reference blank, right? 100% would be just 1. Negative log of 1 is going to be equal to 0. So your absorbance is equal to 0 for the distilled water. Okay? So 100% transmittance means there is no absorbance, and therefore there is no light being absorbed by the water. Okay? So A is equal to 0 for your reference blank, which is distilled water. Now, visible light. So before I move on, let me highlight the equations that you will need. You will need this one. Okay, percent transmittance is I over I naught times 100, or like you should know that one, even though like I will give you the data for this one, you should know in terms of solving an FRQ, okay? And you should know that absorbance is the negative log of the transmittance. Those two things you should know. So if they give you data in just transmittance and you need to make a graph of absorbance versus concentration, you need to turn that transmittance into absorbance. So you just take the negative log of the transmittance and you got your absorbance values. All right. So let's talk about crystal violet. So crystal violet is a compound that is acidic, and it is a dye that can be used to basically stain biological compounds like cells because it attaches to different molecules found in cells, okay? It is a bright purple or violet color. It is very pretty. And we use the reaction between crystal violet and sodium hydroxide to figure out the kinetics of crystal violet fading. That's the actual title of the lab. When you mix crystal violet and sodium hydroxide, crystal violet starts to lose its purple color, which means there's a reaction happening. And the second day of this lab is to figure out what rate order that reaction is for the fading of crystal violet. But before you do that, you have to understand Beer's law, because Beer's law is going to help you understand day 2. Okay? So, crystal violet, purple color compound, very pretty. Okay? And when you are doing Beer's law for a compound, in this case crystal violet, you have to figure out what setting you set your colorimeter to. Remember, in our colorimeter, there are 4 settings, 4 different wavelengths that we have to set our colorimeter to. Now you might be like, why do I have to set it to a setting? Because you are trying to filter out the wavelengths of light. Remember, there's a filter here that filters out the wavelengths of light, right? You're trying to filter out those wavelengths of light that crystal violet does not absorb. And you might be like, well, if it doesn't absorb, it doesn't matter. It does, okay? So let me tell you what wavelength we actually use. For crystal violet, we use the highest wavelength or the peak absorbance or the lambda max, okay, which is around here approximately. I believe it's 590 nanometers. I'm just going by memory here, okay? So we try to set our colorimeters as close to 590 as possible. Now, if you had a spectrophotometer, you can actually set it exactly to 590. But we are restrained by the limitations of our equipment, okay? So you might be like, well, why do I have to set it to that? It's because that is where that wavelength of light is the wavelength of light that is most absorbed by crystal violet, okay? This is the wavelength of light that is most absorbed. And that matters because we want the wavelength of light that is going to be most absorbed, because we want all the other wavelengths of light that are not absorbed, meaning would be transmitted, to be filtered out. So all other wavelengths that can mess with the transmittance, because if it's not absorbed, it will be transmitted and it'll mess with our results. We want all of those wavelengths of light to get filtered out. So in order to get the best results, we use the peak absorbance and we filter out all of the other wavelengths of light that can pass through and give us wrong readings in terms of percent transmittance. Okay, so we set it to 590 nanometers. I think these colorimeters can only be set to 565. So our error is, we have a little percentage of error here in terms of collecting our data, but so far the data has worked out. So we are actually setting it like somewhere right there. Okay, it still works out, but ideally we would want it to be at 590. Okay, so reason one, we want only the light that is absorbed passing through the filter and into the solution, because other wavelengths of light will mess with our data in terms of transmittance. And then secondly, the peak absorbance, or this is called lambda max, the wavelength where you see maximum absorbance is called lambda max. That wavelength is also the wavelength where you will get the most sensitivity to concentration changes. Because if that's the one that's most absorbed, then if you change the amount or the concentration of the solution, you will see less absorbance there, okay? Or if you increase it, you'll see more absorbance there. So this is where it has the greatest sensitivity to the concentration of the solution, to the concentration conc of the solution. That is why we use lambda max, okay? What happens on day one of your lab, okay? I have set up a concentrated solution or a stock solution of crystal violet. Hypothetically, this would have be what, well, not really, but in reality, this is what would have happened if this year wasn't so crazy, okay? So the stock solution is a 24 to a 25 micromolar solution of crystal violet. It is a deep, dark purple color, okay? And then I give you this table that's in these yellow, blue, and purple colors, and I ask you to use the stock solution, which is 25 micromolar, to make 5 solutions of varying concentrations, okay? Solution 1 should have a final concentration of 12.5 micromolar, and it is made using 5 milliliters of the stock solution and 5 milliliters of your water, okay, distilled water. That'll give you 12.5 micromolar concentration. Then you use 4 milliliters of the stock solution and 6 milliliters of water to make a 10 micromolar solution. You use 3 milliliters of stock solution and 7 milliliters of water to make a 7.5 micromolar solution, etc. Okay, until your 5th solution ends up being 2.5 micromolar. So you're just adding to a test tube. I'm really trying to walk you through what would happen in the lab. So you would have a test tube. For the first solution, you would add 5 milliliters of crystal violet, and you would add 5 milliliters of water. And 5 ml of crystal violet, and you mix them together. It doesn't actually just stay on the top like this. It mixes almost immediately, okay? But when you mix them together, you have something that's like a lesser purple than the color you started out with, okay? Make it lighter. Whoops. Let's make it like that purple. So you would have like a different colored solution that is lighter, okay? So this would be like 12.5 micromolar. All right. So this is originally 25 micromolar, and this is 12.5 micromolar. Now, you do this 5 times to get 5 different solutions of varying colors, which is what is shown here actually. 5 different solutions. So this is the 25 micromolar. You can see it's the deepest purple color. It's a stock solution. You can tell from the color changing. This is 12.5. This is 10. This is 7.5. This is 5. And this is 2.5. The lightest one is the one that contains the least amount of crystal violet, which is 1 milliliter of crystal violet to 9 milliliters of water. Okay. And you can tell those different changes. This is solution 1 through 5. So this is 1, this is 2, this is 3, this is 4, and this is 5. So you have 5 solutions of different dilutions of crystal violet now. Okay? Now, let's talk about Beer's law. So you understand now the difference between absorbance and transmittance. You understand what wavelength we are supposed to use, which is lambda max, and for crystal violet is 590, but in the lab we use 565 because that is what our calorimeter has closest to the 590, okay? Then, here is Beer's law. Beer's law tells you the relationship between the absorbance and the concentration. Beer's law is written as A equals this symbol, which stands for molar absorptivity. B is the sample's thickness or the actual width of the cuvette. And C, which is concentration. So let me label those again. A is absorbance. This is Beer's law, okay? This variable is the molar absorptivity. Whoops. Now your lab handout will have more details about what these are, but I'll just say it out, okay? Molar absorptivity constant, which is different for each compound that you will be testing. This is called the path length. And the path length is actually always 1 centimeter. Those cuvettes have a width of 1 centimeter, okay? And this is the concentration. So from this equation, which is Beer's law or Beer-Lambert law, which is the longer name for it, you'll see that absorbance and concentration are actually directly proportional, okay? You might see this as A sometimes. Sometimes you see A equals little ABC, and sometimes you see it as this, okay? Depends on who's making the test or the question. So this is unique for every compound that you will be testing, and it also depends on the wavelength that you're using for that particular experiment, and it depends on the substance. So the substance and the wavelength decide what the molar absorptivity constant is. Path length is just the width of the cuvette, okay? And concentration is just molarity. So the importance of this is that if you can graph absorbance and concentration because they have a linear relationship. Absorbance is on your y-axis, concentration is on your x-axis. Yes, go ahead. It doesn't show up in your email? Try emailing to me. So if you graph absorbance and concentration linearly, okay, absorbance on the y-axis and concentration on the x-axis, you're going to get a linear relationship here, okay? And your molar absorptivity constant is actually the slope of your equation. So we'll discuss that in a second, okay? But you can calculate the molar absorptivity constant by dividing the absorbance by your path length times your concentration. Path length is always 1. So your concentration and absorbance are what determine what your molar absorptivity constant is. Okay, so let's see what happens in this lab now. So you have Bayer's law, you have their relationship, you obtain transmittance values, you know how to convert it into absorbance values. So let's continue. Okay, so continuing on with the Bayer's law lab, I'm at home now, but I'm just doing it in chunks. So if there's a little choppiness, like, forgive me. Okay. All right. So we stopped at looking at the transmittance values, or we stopped right here where we had just looked at the 5 solutions that were our dilutions. And what you would do is you would take those dilutions and you would put them into a cuvette like this. These are like some fancy cuvettes, but you put them into a cuvette like this. You close the cuvette top, and then one by one, you would put it into the colorimeter, and then you would measure the transmittance. Okay, the transmittance value will be read on the little screen that is connected to the colorimeter, and then you can record it in your lab notebooks in regular life. Okay, so here are the transmittance values that we actually obtained last year, I believe. Yeah, this is data from 2019, 2020. Okay, so each of these transmittance values was obtained, and actually in between, just because this is a lab technique video and I kind of want you to understand what's happening in the lab, in between every cuvette being placed in the colorimeter and the transmittance reading being taken, you also have to put the reference blank in, which is just your cuvette of distilled water. So you put your, let's say, 12.5 cuvette in, measure the transmittance, take it out, put the reference blank in, calibrate your colorimeter, and then take that reference blank out before you put 10 micromolar solution in. So in between each one, you have to calibrate your colorimeter to get the most accurate results. Okay, so here are the transmittance values, and as you can see, the highest concentration here, which is 12.5 micromolar solution, has the lowest transmittance, and as you decrease the concentration, you can see the transmittance is starting to increase. So you go from 0.17 to 2.4, 3.3, 5.0, 0.72. So it's a nice increase, like a linear looking increase right here as you are decreasing the concentration. So the lower the concentration, the more light will make it through the solution. Therefore, the percent transmittance will be higher, and therefore the actual transmittance value, which is just percent transmittance divided by 100, will be a much higher number. More light gets through, the more light transmitted, the higher transmittance number will be read on the screen. Okay, then once you have your once you have your transmittance, first percent transmittance, then just transmittance as a decimal, you are now ready to apply the equation to calculate the absorbance value, right? So you have this experimental data right here. Okay, it's not perfect, but it's pretty close. These readings will always work out. Actually, I'm very happy with a very simple colorimeter. So here is the equation for absorbance. Absorbance is equal to the negative log of the transmittance value. So you got your percent transmittance, you divided by 100 to get your transmittance, and then absorbance is equal to negative log of that. Okay, so here are, I have a table here, but actually I'd rather do this in Excel. I set up the tables already, and the graph is ready to take in data. So I have my concentration values here. Those are my 5 solutions. I actually added a 6th data point for no concentration. So this is the last one where there is just water and there is no crystal violet at all. And that should give me a transmittance of 1, because we want our line of best fit in our graph to go through 0. Okay, so here are my transmittance values that correspond to these concentrations. Now I have to calculate absorbance here, which is the negative log of each of these values. So you can actually do that using your Google Sheet. Google Sheets work pretty much the same way as Excel. So you can just do equals, equals indicates that you're going to do some kind of function inside the cell, okay? Then you do negative log of, then you need parentheses. You can just select the cell. You can do exactly what I'm doing on Google Sheets. So you type equal, negative log, parentheses, you click the cell. So the cell name is B3, it's in column B in the third row, so B3. Then you close your parentheses and you hit enter, and it'll calculate your absorbance for you. So even in Google Sheets, if you grab just this corner of the cell where there's like a little square, and then you drag it down, it actually populates that entire column. And I believe in Google Sheets, they ask you now if you want to do that for that entire column. It asks you, oh, do you want to autofill whatever, okay? So it autofills the column. So I had already set up the graph to, um, you know, plot when I entered the data. So absorbance is on the y-axis and concentration is on the x-axis in micromolar. And here are our actual data points represented on the graph, okay? So here are your actual values represented on the graph. You got your 0.137, which has the lowest absorbance. Other than the reference blank, it has the lowest absorbance because it is the lowest concentrated solution. The lowest concentrated solution will absorb the lowest amount of light because there's very little particles in it, right? Compared to, let's say, 12 and a half. So it's going to absorb less light than the concentrated solution, okay? Which is absorbing the most, which is 0.763 as the absorbance value. So the equation for this line, so I also made Excel give me a trend line that's a best fit line. You can do this in Google Sheet. I'm not exactly sure how, but I think you can easily look that up. It's not that hard to look up how to insert a trend line, okay? They may have changed it slightly. I'm good with Excel, I just forget the similar functions in Google Sheets, okay? So you got your trend line, and then you got your equation. You can actually have Google Sheets give you the equation for the line as well. So look at this equation. You got a equation for a straight line, and this value displayed right here on the bottom is actually R square value. R square value, the closer you are to 1, tells you how close your data points lie to the best fit line, okay? So we are very close to 1. It's 0.9983, which is really nice. That means all of our data points are almost on exactly the trend line, okay? So we got some really precise data here. So let's talk about this equation for a second now, okay? I am going to write on the screen, which means I'm going to get rid of this. Okay, so you guys can still hear me. Okay, so oops, almost closed it. So here's my equation. Okay, let's write that down. So this is y equals 0.0622x minus 0.0061. Now, our intercept is really small, so as a value used to calculate, you can just, neglect this. It's negligible, okay? Negligible. So you don't have to worry about the intercept at all. It's such a tiny value. It's not really going to, affect the accuracy of our calculations, okay? Now remember Beer's law is A equals epsilon times the path length, which is B, times C, which is the concentration. So if you have that, we know that absorbance is A, and A is the y-axis, right? And we know that concentration is the x-axis, so that's that, which means you are left with the slope of an equation. So we have y equals mx plus b. We have an intercept. In this case, it's negative. But the intercept doesn't matter, right? So we're just going to ignore that. I'm just going to put a little line through it and really erase it. when we're not really paying attention to that, but we know what our y is, we know what our x is. So this number, which is 0.0622, is actually whatever's left in Beer's law, okay? So the slope m is actually equal to the molar absorptivity constants times the path length, okay? Now the path in all of the experiments that will be given to you is actually equal to 1 centimeter. The width of the cuvette is always 1 centimeter, okay? Which means that you can calculate epsilon by dividing the slope by the path length. So epsilon becomes the slope divided by the path length. But since the path length is always 1, the slope is just equal to your molar absorptivity constant, okay? So that is why this graph and this calibration graph is super important. A calibration graph is a graph that you make based with absorbance on the y-axis and concentration on the x-axis for solutions of known concentration. All of the concentrations of these 5 solutions, these are known, okay? And we obtain the absorbance data for known concentrations so that if I tell you, hey, I have an absorbance value, so let's say I have an unknown molarity crystal violet, let's say X molar crystal violet solution, okay? I don't know what this molarity is, but it has an absorbance of, let's say, 0.5. I can ask you, hey, what's the concentration of this solution? You can literally draw a line here and down and find the concentration of this solution, which will be 8 molar, okay? A 0.5 absorbance value would give you an 8 molar concentration, so a micromolar concentration solution, okay? So this is why this graph is super important. A calibration graph is important so that you can find the concentration of solutions that of unknown concentration by using their absorbance values, okay? Lots of words there. It's very late. Kids, I'm tired. Okay. Now, we know by this that the epsilon, which is our molar absorptivity constant, is actually equal to the slope over the path length. The path length is always 1 centimeter. So all done, epsilon is equal to the slope, okay? Now, epsilon does actually have units. They are basically the units that are present in your Beer's law equation, okay? So path length is in centimeters, and then concentration is in moles per liter. Absorbance does not have a unit, okay? So if you solve for epsilon, if you just solve your Beer's law for epsilon, this is EBC, I'll just say E because it's easier, then this would just be A over B times C. So the units for this is basically absorbance has no unit. Really, it's sometimes calculated in units of optical density, but you guys don't have to worry about that. But basically the units for epsilon just comes from the path length, which is in centimeters, and concentration, which is molarity. So that's just going to be E equals BC. So whatever number is going to be units of molarity and path length. Since they're both in the denominator, that's going to be molarity, and path length is just centimeters. Okay, so those will be your units for the molar absorptivity constant. All right, so that's it for the day 1 walkthrough of the the fading of crystal violet lab, and the introduction to Peir's law, day two coming up.